Welcome to Who's in STEM. I'm Ken Ono, your host and the STEM advisor to the Provost and the Marvin Rosenblum Professor of Mathematics at UVA. Our goal is to evoke flights of imagination and wonder by showcasing the cornucopia of all that is STEM at UVA, the marvelous world of UVA science, technology, engineering, and mathematics. As a mathematician, I like to say that math is everywhere. I revel in the fact that math is the language of science. And in my research, I occasionally venture into the realm of theoretical physics. With collaborators, I've pondered abstract objects with strange names. Conformal field theories, monstrous quantum gravity, stringy black holes and K3 surfaces. Now, as exciting as these objects might be to me, they're exotic, and they're just bit players in the gigantic world of physics. You see, physics is extraordinary in its breadth, and its mission is daring. If you ever thought of scientists as being daring, the physicists are among the most daring you will ever meet. Where's the proof? Just look at the questions that they ask. What's the nature of matter? What are the laws of energy? What's the nature of space and time? And as simple as the next one might sound, it's incredibly difficult. What's gravity? Physicists want to understand the essence of nature itself, which, well, they'll tell you, that's everything. And as old as science itself, physics, despite its age, continues to thrive, pushing boundaries of understanding and application. Present-day practitioners are intellectual descendants of Galileo and Kepler, and perhaps of the familiar more modern names that you'd know. Think Albert Einstein, Stephen Hawking, and Richard Feynman. I'm proud to say that even though I'm a mathematician, I'm a direct descendant of Feynman. My PhD advisor, Basil Gordon, earned his Caltech PhD in physics and mathematics from Feynman and mathematician Tom Apostol. But more generally, I said before physics is booming, you see the abundance of groundbreaking news stories are proof. Let's see. Maybe some of these will sound familiar to you. The discovery of the Higgs boson, aka the God particle. The discovery of gravitational waves. And everything you hear in the news about everything quantum. Do these things sound familiar? Now, as extraordinary and as broad as physics is, it won't then come as a surprise that there are many kinds of physicists. And who are they? They're often the high priests and priestesses at places like NASA, CERN, the largest particle accelerator in the world, and at Los Alamos, made famous by Robert Oppenheimer and the Manhattan Project. Maybe many of you saw the film. And of course, our physicists are often the high priests and high priestesses at research universities, like here at UVA. It's in this spirit that it is my distinct pleasure to feature in conversation today two exciting UVA physicists. Marija Vucelja is an internationally acclaimed physicist, well known for her work on the Mpemba effect. It's really a fascinating thing. It actually sounds like it's not possible. It's the fascinating observation that hot fluids can sometimes freeze faster than cold ones. Sound crazy? And we're also happy to have with us today David Nichols, an astrophysicist who detects black holes from gravitational waves. Marija, David, welcome to Who's in STEM.
Thanks for having us, and thanks for that wonderful introduction to physics.
Thank you. I'm an avid follower of your show. I've listened to it from the first episode.
Oh, thank you very much. That's great plug. Well, welcome to the show. First, for both of you, physics is really quite broad, and I think the perfect place to start is, as faculty members, what can you tell us about what's going on in UVA physics today?
Well, before we get into physics, I think one interesting thing that is going on in physics is there's been a lot of disruption along McCormick Road in front of the physics building, and that's because our physics building from the 1950s is being upgraded and renovated to be fancy and new and wonderful. So at the moment, The physicists are scattered all across campus. I'm in astronomy, people are in chemistry and biology, but we're going to reunite after the second phase of construction ends in January. And we're looking forward to being in a nice new and updated building.
Yeah, if I understand it correctly, the construction, the renovation is going, as you said, in 2 phases where you've literally split the building in half. One half will be renovated properly and beautifully, and when that renovation is complete, the other half, is that right?
That's right. It'll be a little bit of a two-face moment that there'll be the upgraded fancy version and the phase 3, which will happen in the future. But within hopefully a year, the entire thing will be finished and we'll all be united in the building again. And
have you peeked behind the curtains to see what it's going to look like? Is there?
Oh, yes. It's going to have in the central part, there will be a large open space. And I think it will be more somehow collaborative. Right now, it's a very standard building with long corridors. Well, right now it's construction, but before that, it was a standard building with long corridors from which you could go into small offices and never see each other. Afterwards, there's going to be a big open space.
Where the professors can collide, pun intended.
Yes.
Well, so in addition to the building, which is exciting, what are some of the recent breakthroughs that UVA physics has produced? What are some of the fancy things your colleagues have been producing?
My colleagues span almost the whole of physics. In our department, we have people doing optics, nuclear physics, biomedical physics, there's astrophysics, high energy physics. I shouldn't forget my own sort of hard condensed matter. And between us, we cover, I think, from the smallest to the largest particles and phenomena.
That's fascinating. How many faculty members are there in the physics department?
So there's 35 faculty in physics. And like Marija said, we study scales from the size of the entire universe to below the size of a proton. So we cover essentially all scales. And then we cover the coldest temperatures. So just a millionth above absolute zero to essentially the hottest temperatures that occur maybe just a few seconds after the Big Bang. So we cover all the different scales, all the different temperatures, and as a result, we have a lot of different people working on special topics because no one can really cover all this on their own.
I'd like to talk about your individual research projects. David, you study black holes and gravitational waves. I don't know where to start except to say, what are gravitational waves and why do they matter?
Yeah, it's a nice 2-part question. So what are they first? You have to step back from what are they to describe what is gravity, actually.
Good question. I know if I drop this iPad, it'll break, and I'll be really unhappy with gravity.
Yeah, we're all familiar with gravity on Earth, but gravity exists all throughout the solar system and the universe as a whole. And Newton was the first person to really think about what is gravity, and he described it as a force that acts instantaneously between 2 different objects, the sun and the earth, for example, and it just is proportional to the inverse of the distance squared between the 2 objects. But Newton even thought that the gravitational force was incomplete because he didn't really describe what it is. He just said, there's some invisible, instantaneous, acts immediately force that causes the sun to stay at a fixed point and the earth to go around it.
And his predictions were actually mathematical laws which helped us discover Pluto and Neptune through observation.
There was one puzzle, which was Mercury.
Yeah.
Mercury was kind of the oddball that when it was going around the sun, its orbit was just drifting a little bit more than people thought. So for a long time, it was hypothesized that there was a planet within Mercury called Vulcan. But as telescopes got better and people looked for it more and more, it was never found.
Actually, I know the story. I think some people even observed Vulcan on the telescope and they ended up getting laughed out of science. Although Vulcan does exist on Star Trek.
Yeah. So it is something of science fiction, but not science fact at the time. So what Einstein did that was really remarkable is he completely reformulated what gravity was. He had sort of answered Newton's question of what is causing the Earth to go around the sun. And it turns out that gravity is the distortion of space and time itself. So this is kind of a wild thing to think about, that both space and time get distorted by the presence of a heavy object like the sun or the Earth. And there's a nice way of summarizing the theory of relativity, which is actually due to John Wheeler, which is Feynman's PhD superadvisor, since you mentioned Feynman earlier. So Wheeler had this nice quote that said, mass tells space and time how to curve, and space and time tell mass how to move. So there's an interplay between how space gets distorted by mass and how mass moves around in space and time.
So the relativistic effects of the sun did away with the problem about the absence of a planet called Mercury has much less impact when we start talking about the scale of where Pluto is and where Neptune is.
What you notice is that gravity only changes significantly from what Newton predicted when objects are very dense, are very compact, let's say, compared with the Earth. So if you crush down the sun by 1/1,000,000th of a size, then you'd start noticing the effects of relativity even stronger. And the reason I mentioned that is because that's an object like a black hole would have roughly that size.
So these gravitational waves, how does that relate to this theory?
Yeah, so interestingly, 1 year after Einstein wrote down his theory of general relativity in 1915, he predicted something called gravitational waves. So whenever a mass moves, because gravity, space and time is something physical, then it doesn't respond instantly. It takes some time for space and time to notice that the mass moved a little bit. And it turns out the speed at which it propagates is the same speed of light that we're familiar with, that radio waves, our Wi-Fi, light from the sun, they all propagate at the same speed of light. So space and time distorts at the same speed of light. Whenever you have something moving around in space and time, then you can produce these ripples in the curvature of space and time itself, so these distortions that propagate out. And they have the unusual property that they cause space just to stretch a little bit in one direction and squeeze a tiny bit in the other direction. And Einstein, in fact, even calculated how big would the stretching and squeezing effect be from two stars like the sun just going around each other. There's a lot of pairs of stars in our universe. And when he did the calculation, he estimated as roughly 1/1,000,000th of the size of a proton. So he thought, this is hopeless, but this is not even any advanced technology can really detect this.
This is 100 years ago, though.
Yeah, this is 1916.
Right.
So, yeah, I can flash forward then 50 years, and in the 1970s, people realized that there were things like black holes, so stars that collapse, like the sun. The sun won't collapse to a black hole, thankfully, but a star, say, 100 times more massive than the sun will. And it'll crush down to an object that's only about 60 miles across, 100 kilometers, if you prefer SI units. So these are, these are extremely dense things. This is something that weighs, 100 million times the mass of the Earth, but is crushed into something that's, roughly the distance between here and Richmond, let's say. So this is, a wild object. And it turns out if you get two of these black holes together, they can make gravitational waves that are, millions to billions of times stronger than what Einstein predicted. But even that means that the kinds of distances you need to measure are extremely tiny, still a 10,000th of the size of a proton. So what was remarkable was there were a lot of developments in precision measurements, so measuring extremely precise distances due to extremely precise light sources like lasers and very low noise counting of light, so so-called photodetectors. With these two developments, you could actually build a detector. It would have to be several miles large, but you could still actually build something that could, in principle, detect gravitational waves. And the main players who were interested in this were Ray Weiss at MIT and Kip Thorne and Ron Drever at Caltech. So Kip Thorne's name you might have heard because he was one of the executive producers on Interstellar. So he's thought both about science fact very seriously and science fiction.
And he's actually like your image of cool physicist, right?
Yeah, exactly. I actually wrote a couple papers with him when I was doing my PhD. So it was, wonderful to work with him.
And so why do these gravitational waves matter? Do you view it, and this is Nobel Prize winning work, and as you say, it also requires a lot of new mathematics. We gave out an Abel Prize to Yves Meyer for his work on wavelets, which goes into some of the mathematical aspects of this work. So why do gravitational waves matter? Is it as simple as Einstein made a prediction and this is further evidence for it? Or would you say it goes beyond that?
Yeah, I'd say it definitely goes beyond that. So What I like to think about is two black holes, or there's another very dense object called a neutron star, which is basically like a giant nucleus that weighs the mass of the sun. Two of these objects are colliding about every 10 to 15 minutes in our universe. And before 2015, when the first gravitational wave from two merging black holes was discovered, this was happening every 15 minutes, but we just never knew it was occurring. We had no way of measuring this. So once these detectors turned on, and it was actually sort of immediately after they turned on to their initial design sensitivities, we saw the merger of two black holes occurring. So it opened up a new window to observing the universe that just hadn't existed before. And what are some interesting discoveries that have come from this relate to the properties of matter at its most dense. So similar to understanding, what the composition of a proton is, the composition of a neutron star is similarly dense material. And when two of these collide, they actually make all the valuable heavy elements that we're used to. So things like gold and platinum, these come from the collision of neutron stars. So we learned about the abundance, how much gold and platinum there are in the universe from these collisions of neutron stars that we measured through gravitational waves and through related electromagnetic counterparts. And there are other fun things we learned just about the nature of gravity itself that we couldn't measure from other things, including things like the expansion of the universe. We were able to make surprisingly precise measurement just from one event of this collision of neutron stars. So it's really opened up a new window into how we can understand the universe that didn't exist, a decade ago.
Thank you, David. Marija, you've been in the news. Congratulations. Tell us why.
Thank you. I like to study systems that are far from equilibrium. Now, you might think this is exotic, but they are actually everywhere around us. Maybe it's your coffee and milk mixing together in a cup, or, for example, a balloon where you pierce a hole and suddenly you have this air currents and pressure mixing, or a soda can next to an ice bucket. So if you think about the soda can next to an ice bucket, they start exchanging energy with each other. And slowly they exchange energy, and with this energy exchange, its conduction through the aluminum wall of the soda can, they get to a state where they're both happy, thermal equilibrium, where there is one temperature. Most of our intuition is from there. So whenever you have something puzzling, sometimes it's newsworthy. These kind of conundrums are newsworthy. In particular, what caught the attention in the news was my work on this puzzling phenomenon called the Mpemba effect. It's the effect where a system that's prepared at a hot temperature cools down faster than a system that's prepared at a warm temperature.
Yeah, let's say that again. So imagine a pot of boiling water freezing faster than ice water. That sounds impossible.
It started with water. In fact, even already Aristotle showed it, that mentions it. So this puzzle is 2,000 years old.
I didn't know that.
So Aristotle says that if you want to cool something effectively, you better start by putting it in the sun. Then there are other people that wrote about it, like René Descartes and Francis Bacon, with similar observation. We rewind all the way to the 60s, and we come to Tanzania. And we have a secondary school boy called Erasto Mpemba, and he is doing something very important. He's trying to make ice cream faster. So he has an ice cube tray with milk and sugar, and he's just putting it in the freezer. And he observed that he can, with lukewarm milk, he can make ice cream faster. Now, you cannot deny that science of making ice cream faster is important.
Yeah,
right?
Yeah.
So then later on, he measures it together with a colleague, Dennis Osborne, and they find out that hot water freezes faster than cold.
Now, what was the response for him? I mean, did he fail his middle school class? Did he have a teacher that said, hey, you did something wrong?
His class laughed. They called it Mpemba physics. And then, well, I guess the answer comes, how many years is that from the 60s? So maybe around 60 years later. Many people are talking about the Mpemba effect and Mpemba-like effect, so much so that it's an active and emerging research direction, and it's a part of what I like to think about, non-equilibrium statistical physics. So with colleagues, what we did actually, we predicted a new regime where this Mpemba effect is some sort of a shortcut. It's a shortcut where your underdog wins in some sense, if you want. You have one system. Mpemba did it with water, but by now we know it works with magnets, with polymers, with semiconductors, you name it. It's a general phenomenon.
Mm-hmm.
So the effect is some sort of surprise, a shortcut in a relaxation, somebody who's further off. It's easy to think about temperature. Hot system should not cool down faster. It's counterintuitive that it cools down faster than a warm system. And in my work, what we did, we found a new regime where this relaxation shortcut can be exponentially faster. And there's a jump in the relaxation time. And you not just that, you go through this, through your target state from a different direction. Let me give you a cycling analogy, since I know you like cycling.
Yeah, if someone could give me a shortcut to training, that'd be great. I want to be the Mpemba effect to fitness.
I don't have one for training, but you might call it cheating by the time I finish talking. But here's how it goes. Here's how I think about it. Suppose you have a racetrack, so a cycling track. You have your warm guy. He's at the beginning. And the racetrack, towards the end, there is an uphill. So everybody who starts, he's going to kind of slow down. Now the hot system, the underdog, he starts from a different place. He starts further away. But in this strong Mpemba effect, he has found a secret. He never goes through the uphill to reach the finish. His direction to the finish is a mountain ridge. So he goes there faster. Mm-hmm. Okay? So we actually managed to quantify in certain systems, they are kind of toy models for glasses and disorder system called random energy models. We managed to quantify how often do you have these shortcuts and where they are. And so how often was important because you don't want a needle in a haystack. Right. You want something that people might be able to use.
Who would have thought that beginning with making ice cream in the 60s, that we would have come this far. So our time is quite short here, but I do feel like one term that comes up all the time in pop science is quantum stuff. Quantum mania, quantum physics. Quantum mania happens to be the stuff of Marvel movies. In my side gig, I do a little bit of work occasionally in film. I was actually asked to produce the mathematical and physics equations for this film called Ant-Man and the Wasp. So if you've ever seen this film, you might remember a scene in the professor's office with some equations in the back. That was my work. That was super fun. But back to reality, quantum mania, which was the inspiration for that film, is real life stuff. It's very important. So what do we mean when we use terms like quantum physics and quantum mania, and why might that matter to us in our day-to-day lives? I'll start with you, David.
Sure, yeah. So when you think about very small particles, they don't behave like, big things on Earth that follow just Newton's laws. They have weird probabilistic effects and other weird phenomena, like they can act as if they're in two places at the same time. So there are things that are completely unintuitive. And now at least we have a good theory of quantum mechanics for how this works. So we're thinking about what are all the applications? How can you use these weird quantum phenomena to, say, for example, build better computers? Or
a quantum computer, yeah.
Exactly.
Tell us about that. If someone makes a quantum computer, what are some of the consequences?
Yeah, well, one thing that people are very worried about is quantum computers are very good at factoring large numbers. And I know as a mathematician, you can appreciate that.
Yeah, I'm really worried about that. Yeah.
But it turns out that anytime you type in your password to make a secure transaction, then this is actually encoded in a way that depends on factoring very large numbers.
Or the inability to do this quickly.
Exactly, yeah.
Right.
That's a better way of saying it, is the fact that you can't easily do this, that it's a challenging problem. So if a quantum computer can do this very efficiently, all of a sudden we're in big trouble because all of our secure banking transactions and other financial transactions will be available for people to snoop on and steal and so on. So there's a big race to essentially develop a quantum computer first, because you'd like to be the one who has this technology. So there's a lot of interesting things happening in this quantum computing direction. And there's a lot of other different directions in quantum physics. There's still unknown fundamental physics problems that people at the Large Hadron Collider that you mentioned earlier, who discovered the Higgs boson, we're still just trying to understand some fundamental quantum properties of these new particles. So there's a wide range of quantum phenomena that physicists are involved in here at UVA.
Yeah, thank you, David. Marija, would you like to add to this discussion of all things quantum?
Of course, we also, at the physics department, we also have Peter Schaus, who is able to put atoms in optical lattices and design interactions between them. And
he's playing with the atoms.
He's playing with
like
atoms.
Like on a little chessboard.
Exactly.
Didn't Einstein say God doesn't play dice with the universe, but your friend Peter plays checkers with atoms?
Well, Einstein has had his quarrels with quantum mechanics, but...
That's what I was getting at.
We'll forgive him for that because he had a lot of other things right to say. But with this optical setup, you can study some things which you can't, because of scale, study in solid states. So you can use optical systems in order to design interactions as you wish between, you can think of it, this is like in some sort of an container where you hold your eggs, and in each of them you can put an atom and you can design how close they are and how do they interact with each other, essentially. So you can create artificial systems which can then tell you something about some condensed matter systems.
Yeah, that's fascinating. We should have Peter on the show to learn more about that. Thank you very much. I want to switch to this last topic. I think it's kind of important. We frequently hear, and in fact it came up several times this summer, we hear about controversial breakthroughs in physics, say cold fusion, or the development of a superconducting material, or things that seem to populate our news cycles over and over again and often end up going viral only to vanish or end up not panning out at all. First, why do challenges like cold fusion and superconducting, what are they and why do they matter? David?
Yeah, so fusion would be a remarkable energy source, right? It would solve basically all our energy problems because you take, say, 2 or 3 hydrogen atoms, you bring them together, and you get a lot of energy out, and it produces, essentially helium as the output, so a completely harmless gas. So that would be great if we could tap the potential of fusion. The problem is that standard approaches to fusion require a huge amount of energy to come in for the hydrogen atoms to come together and overcome their natural repulsion because they're both positively charged.
Right.
So you needed these very high amounts of energy. So going back to the 80s, there have been claims that certain kind of catalysis, chemical type reactions might be able to produce cold fusion, but these have never panned out. So that's, one thing on the cold fusion side. And then there's this other challenge
but
about...
I think we should add about cold fusion. What's nice about it, if you compare it to fission, is it's not a chain reaction. You pull the plug, you have no more this electromagnetic trap which was keeping those hydrogens together, and it stops.
Right.
So not just that the product is harmless, also if you want it shut, you can stop it.
Everyone's afraid of that, right? And that's the source of the excitement, because if someone does produce cold fusion, where cold even doesn't have to be that cold, would be remarkable.
And then the other part of your question about room temperature superconductors, those would be another wonderful thing to have because they would allow for extremely efficient energy transport on the electrical grid without waste. Because currently superconductors have to be cooled to several hundred degrees below zero on the Fahrenheit scale, which requires nitrogen gas, like in our atmosphere, bringing it to a liquid as opposed to a gas state. So it would be great if you could come up with a room temperature superconductor, but there's difficulties in reproducing some of the results that have been recently claimed. So there's a lot of discussion, which is probably what you saw in the news recently.
And then the journalists like to talk about fighting and bickering scientists.
I mean, this is just how science is conducted, that we put out hypotheses, we try to convey our results as accurately as possible, but people do sometimes make mistakes. And these mistakes usually are caught, and they're usually made not with nefarious intentions or something. They're usually just accidents, and it's often embarrassing when you make a mistake, especially on a big claim, to have to correct yourself, right? But it's ultimately what happens, because if you can't produce it, science is a self-correcting organism, if you'd like to say, in some non-biological sense. The truth will come out eventually. So this is kind of what's happening in real time, and it's not something that people always are familiar with. They're used to reading about Newton discovering gravity 300 plus years ago, and it's all settled. But in fact, when we do our research, we sometimes make mistakes and we sometimes go down the wrong path. But ultimately, there is remarkably this sense of progress in science, that we keep moving in the right direction, building better technologies and correcting the mistakes that happen along the way. So.
Right. I mean, like for Newton, what if it was a super windy day when that apple fell, and instead of falling, he didn't see it at all, right? Maybe we're still trying to figure some of that out.
You're touching upon something really important, that when we look at the past, we look at the results. And when we look at contemporary science, we look at the research process itself.
Last question. Interested students that want to get involved in the various physics activities, clubs, research, etc., how can they get involved?
Do not be shy. Try to knock on doors and ask questions. Scientists lit up if you ask them a question about their research. And really, you don't need a lot of advanced knowledge, prior knowledge. For example, in what I do, which is statistical physics, I would say calculus 1, 2, 3 plus some probability, some coding experience takes you a long way. And the reward is amazing. The reward that you get is you learn that it's not the answer that we are searching for. We are searching for the question. It's much harder to find a good question, an interesting question to work on than to find an answer. Sometimes both our question and our answer morph while we are researching it. And I think it's a valuable skill to learn.
David, undergraduates or prospective UVA students, if they're interested in physics, what can you offer them?
Yeah. So I would suggest getting in touch with the Society of Physics Students. It's basically like a big physics club here at UVA. And they actually even maintain a list of research projects where undergraduates can get involved. So they're not always up to date. So I also recommend doing what Marija is saying, is after you read these and you get in contact with people, maybe the project's a little out of date. So just also talk to the faculty themselves. We're always happy to answer questions, and we like talking about our research. So it's
and the group again is called the Society of
Physics Students.
Physics Students,
SPS.
And there's a website that's accessible from the physics department page.
Yes, it's
Great.
linked to the physics department page. And I would also just recommend, it's often easier to get involved in experimental research when you're starting off, because it doesn't require as much coursework. So if you have some hands-on skills, like you've ever soldered before, or these kinds of things.
Good with a wrench.
Or if you took, some programming classes and you know how to read data and plot it, these kinds of things, you can already get involved without so much coursework. And I think that's, a nicer way to get involved. And also don't be afraid to, try a few different projects. One thing might spark your interest and later you get more excited about something else. I probably worked on 3 or 4 different topics before I ended up getting excited about astrophysics and black holes.
Well, Marija, David, thank you very much. This was a super fun conversation. You're both fulfilling President Ryan's vision for UVA to be great and good in all that we do. Thank you for your commitment to pushing the frontiers of our understanding of the world. I'm Ken Ono, STEM advisor to the Provost and the Marvin Rosenblum Professor of Mathematics, and you've been listening to Who's in STEM.
Who's in STEM is a production of WTJU 91.1 FM and the Office of the Provost at the University of Virginia. Who's in STEM is produced by Catherine Kossaboom, Claire Curzan, Ria Verma, Mary Garner-McGee, and Ariane Ballou. Our music is composed and performed by Robert Schneider and John Ferguson of Apples in Stereo. Follow us on Facebook, Instagram, and Twitter. Listen and subscribe to Who's in STEM on Apple Podcasts, Spotify, or wherever you get your podcasts. We'll be back soon with another conversation about scientific and technological innovation at the University of Virginia.